Hello guys and welcome to another video. This video is going to be kind of like a recap to Ethernaut where I'm going to be sharing my learnings that I had with each of these 29 levels in Ethernaut. Of course, if I make a detailed video, this is going to be more than a half video. So what I'm going to do is I'm going to share bits of information that I have collected throughout these levels and how I solved each of them. Also, here I have this markdown file which contains information of all the learnings that I had while solving these levels. I will provide the link to the GitHub for this markdown file. So as this is going to be a long video, let's get started right away. And the first one is going to be fallback. So the goal of this level is to drain all the funds that are within this contract. And to do that, the only way is to become the owner. And to become the owner, we need to call this receive function by sending our ether value here. And obviously, the learning we had here is how to call the receive function. Personally, how I solved this was using Remix to send an ether. You could also use Ethers.js or Web3.js by using the browser console. Let's go to the next one, which is going to be Fallout. So the major learning I had at Fallout was to identify the silly mistakes people could make while writing the contract. For example, in this contract here, this function is named as the constructor, but this is actually a normal function. So the goal of this contract is also similar where we need to drain the funds. And to drain the funds, we need to become the owner. And we could easily become the owner by calling this Fallout function, which is commented to be the constructor. So the next level, the level number 3 is going to be coin flip. So the major learning at CoinFlip is that there is no way to get real randomness in the blockchain because everything is deterministic and everyone can view them. The way we learn that is through this flip function where we need to make a Boolean guess, and the randomness here is created by the block hash and block dot number, which is visible to everyone. And the thing is, we need to guess the right value for 10 consecutive times. And the easiest way to do that is just by copying this function, whatever code that is in this function, and create a new contract and pasting it there. And from our contract, we can calculate this guess, and from there, we will call this contract. And the next one is going to be telephone. The telephone one is pretty straightforward. We learned the difference between transaction.origin and the message.sender. And the way to solve this is to create a contract and call this function where the contract would behave as the message.sender and the externally owned account is going to be the transaction.origin. And the next one is going to be token. So token, we learned the importance of an order issue in Solidity, which was underflow and overflow, which was corrected in, I believe, Solidity version 0.8 of the compiler. So here our goal is to drain all of the funds available here, but we are only given with 20 tokens. And here in the transfer function, we have this check of that whenever we use this transfer function, our balance should be more than zero after subtracting the value. So here we did not do any overflow and underflow checks and the version is 0.6. So there is underflow and overflow. And what happens is if we give a higher value, if it subtracts from this mapping, which is going to be UN 256, it is going to underflow and cost the maximum value of UN 256. So whenever any higher number is given here, it is going to be greater than zero and it is going to bypass and we can withdraw all the balances that are within this account. So the next one is going to be delegation. Delegation is also an important one because here we learn what are proxy contracts and what is delegate call. We learn how the state changes at one of these contract can affect the other because of delegate call. Here our objective is to become the owner and to become the owner we should call this PWN function which will change the state here and it will also affect the state here. And here we also learn that in the delegate world, we need to pass in the message dot data of this function. So here we learn how to get the function selector of this function and pass it as the message dot data. So the next one is going to be force. Force is pretty straightforward. Here there is no code, but we need to send ether to this contract. Generally, if a contract does not have a receive function, it will not receive any ether. but there is one bypass to this, that is by using the self-destruct function. So to solve this, we need to create a contract which will have a self-destruct, and from there we can easily send ether to this contract. So the next one, which is Ethernaut number 8, is going to be vault. So here we also have a major learning that there is no privacy in the blockchain. Even if the variables are set to private, we can easily read them. Here our goal is to get this locked to false, and the only way to do that is by knowing the password. To know the password, we need to get through this private variable. We can easily do this by using the browser console and using Web3.js to get the private variable. And the next one is going to be King. King gives us an introduction to the denial of services attack, and it is also based off a real life hack which happened to the King of Ether game. This piece of code is the simple version of the game, and I'm not going to go too detailed into the mechanics, but the summary of our objective is that we need to become the king, and we should not allow any other person to become the king, even if they meet the requirements. So here you can see this receive function, which is the main function which allows other users to become the king. Here in the second line, for anyone to become the king, they need to transfer us the message.value. Here they are sending the value to the previous king. In this case, we are going to be the previous king. And in our contract, we are not going to have a receive function. This will make this piece of line fail. So after this fails, this entire function is going to fail. So due to that, we are denying any user who tries to become the king. Because if our receive function, this transfer method fails, no one can become the king. Okay, then our next level is going to be reentrancy. Reentrancy also gives us an introduction to another important hack in Solidity, which is the reentrancy attack. Here also, I'm not going to go very deep into the mechanics, but the major learning we have here is the checks, effects, and interaction pattern. It states that first we need to do the proper checks, and then we need to do the corresponding effects, and after that we need to finally do the interactions with any external contracts. Here, this piece of code is like a bank contract where we can deposit and withdraw money. Here, if you look at the withdraw function, first it checks if the user has the appropriate balance, and then it sends the user value. So this is the interaction part where it calls and sends the ether to the user. And finally, after all this, the balance is updated. So this is the effects. So here you can see that it does not follow the checks, effects, and interaction pattern. It does interaction before effects. So we are going to exploit this and drain all the funds. How we did this is we are going to be creating a contract, and in that contract we will have the receive function. So in this line it is going to call the receive function, and in the receive function we are going to have a piece of code which is again going to call this withdraw function with that appropriate amount. As we are doing the effects at the end, we are doing the state change at the end. At this point, the balance is still high, and because of that, we can call this function again and again, and it is going to loop, and we'll be doing that till the contract is drained. Okay, that's all about this contract. Next, we're going to the next one, which is going to be elevator. Elevator is a simple level where we learn that whenever we are using an interface and we are allowing user to have the contract adhering to the interface, we need to be very careful when designing these functions. And also it gives us the importance of the view and pure visibility modifiers. So here we have this building interface, and then here we have a function. So our objective is to get to the top floor, and we have a restriction that only if we are not at the top floor we are going to get inside this piece of block. To bypass this, we can see that this same function is called twice, and we need to give false for the first time and we need to give true for the second time. So as you can see here, this function is last floor, does not have any visibility modifier such as view or pure. So we can do state changes, and due to that we can design a simple loop or a counter where the first time we're going to return false, and for the second time we're going to return true, and we can solve this particular challenge. And the next one will be the privacy. Privacy is also similar to the challenge vault, where we have read the data in the blockchain, which is set to a private variable. Here we are going to be going a bit in depth and going to be learning how the array variables are structured and also how the 256-bit slot is going to work. Here we can see that we have uint 8 and another uint 8 and uint 16. Here we learning that the smaller sized variables will be clumped together into a single slot. Here both this uint 8 and this uint 16 will be present in the same storage slot. Next, we'll also be learning about the conversion between bytes 32 and byte 16, and that's all for this challenge. The next challenge is going to be Gatekeeper 1. The structure of Gatekeeper is that there is this function, and to enter this function, we need to get to three gates. The first one is very simple because we already know the difference between the message.sender and the transaction.origin. We can easily bypass this modifier using a contract. The next one we have the gas left function. We'll be learning about how this functions and how to use this. There are two ways to get through this modifier. One is to find out all the opcodes and the gas utilization and come up with the exact value. Or we need to brute force and get the amount of gas we need to give into this function to arrive at the gas left value, which is going to be a multiple of 8191. So I used the brute forcing method, and it was the first time I used brute forcing in Solidity, and I learned a lot. And coming to the third modifier, we have the K3. Here we will be learning about the conversions of types between bytes and UNs, and inside UNs also we'll be converting between UN64, UN16, and UN32. The major learning have here is that how these values are affected whenever they are converted between different types. And we should be taking some time to engineer a perfect gate key, and we can easily get through this modifier. And the next challenge will be the Gatekeeper 2. Gatekeeper's 2 structure is also the same as Gatekeeper 1, and here the modifier gate 1 is the exact same. So let's skip on to gate number 2. Here, this is the part where I spent a majority of my time because this is the first time that I have encountered inline assembly in Solidity. Before this, I had no prior experience working with inline assembly, so I had to learn what was the syntax like, and why it is used. So here specifically we have this code size call which takes in a contract and checks the size of the contract. Here we are loading the size of this contract into this variable x, and we have a require statement which requires that the size of x should be 0. One of the way to achieve that is before the contract creation, every contract is going to be size 0, and we are going to be making this function call before the contract during the contract deployment in the constructor. So when we are calling this function in the constructor, the contract has not been yet created in that transaction, so the size is going to be 0. And coming to finally the gate number 3, here we'll be learning about the bitwise operators and also the type UN64 max. So this one is simple because type 64 max is going to be giving us the number which the highest value that UN64 is going to hold. And as I also previously known about how the bitwise operators work, here we have this XOR operator to arrive at this type, I mean, even 64 max value. I use the NOT gate to engineer the gate key to come up with this value. Moving on to the next challenge, we have Notcoin. Notcoin was a very simple one for me because I already know the ERC20 standards. So the aim of this challenge is to give us a introduction to the ERC20 standard. We when we go through this challenge, we learn how the ERC20 standards works. Here we need to transfer the token given to us, and we are limited by this transfer function which has a time lock, so there is no way to get around this. But as we already know how the ERC20 standard works, We'll be utilizing the transfer from function, which is also available without any log, and we'll be transferring the amount. Next is going to be the preservation. Preservation is also similar to the previous level where we use the delegate call. Here is also a proxy pattern. Here we have two contracts, and the major learning we have here is how the alignment of the storage slot is going to affect us. Because here you can see in this preservation contract, the first slot is the library, but here in that library contract, the first slot is the stored time. So from this library contract, preservation contract, we are going to be calling the library. And just because we have a different variable alignment issue, when we set the time, we're going to be setting the address for this one library. So we are going to be creating a contract which will have many variables, and the third one is going to be the owner. And also the goal of this challenge is to become the owner. And as we're going to create a contract, we can easily and also we'll be learning the conversion between event and address. We are required to convert our contract's address into an event to solve this particular challenge. This one also was quite easy, and we need to simply change the time into this address, and from our contract we need to change this owner variable. And going on finally to the final challenge for this particular video, which is recovery. Recovery was also a short one for me because here we have a contract which deploys a contract, and the address of the contract is nowhere stored here. Our goal is to retrieve the address of the contract. So because I already have used the block explorer, it was an easy one for me as I went to the block explorer and went on to this particular transaction and went inside the internal transactions and found this address of this simple token. So it was a simple job. I think this is going to be the end of the video because it has already become a large video. So thank you guys for viewing this video. The next part will be the part where I explain every remaining challenges of Ethernaut. So thank you guys and be subscribed.